Hello, my name is Sushant Surendra, and today I will be discussing about my course project for EEL 6512, which is determining the time from the image of a clock using MATLAB. To begin with, the idea behind this project was to develop an algorithm which will allow the computer to read the time in an attempt to emulate something which is very simple for us owing to a superior visual system. We as a human being can easily read the time, but when the same needs to be emulated by a computer, the process is not as simple as it sounds. The absence of a proper computer vision algorithm may render the computer useless when it comes to this front. Using concepts which I will discuss in the forthcoming slides, this algorithm discerns the hour and the minute hands in a clock and determines the required points and angles using coordinate geometry. Apart from this, the scope of the project is also extended to situations where the image is corrupted by noise. Such situations require pre-processing such as image filtering and image enhancement techniques, which will clean the image to a satisfactory level. In general, this project discusses two situations where the image of the clock is riddled with salt and pepper noise, or when the image is affected by a motion blur. Now, the key concepts that I have utilized in this project are as follows. First one is the hue transform. The second is the edge detection, more specifically the canny edge detection algorithm. Third is the median filter, which is used for cleaning the salt and pepper noise, or as it is commonly known as the impulse noise. Fourth, the Wiener filter, which is used for deblurring an image that has been affected by a motion blur. And finally, contrast limited adaptive histogram equalization, which is used for enhancing the contrast of an image. A hue transform. All straight lines in a plane can be represented by two parameters. If a parameterization is fixed, then any straight line can be represented now as a point with a new parameter space. Fundamentally, this is the concept on which the hue transform works. It works by using the parameter representation of a line, which is given by rho is equal to x cos theta plus y sin theta. Here, rho represents the distance from the origin to the line along a vector perpendicular to that line. It is represented by the blue line in the image, whereas theta is the angle between this vector and the x-axis. In MATLAB, this hue transform is realized using the hue function. It is also readily available in the image processing toolbox. The hue function generates a parameter space matrix which contains various rho and theta values as its rows and columns respectively. Now, the peak values in this parameter space matrix, which correspond to potential lines in an image, are located using the hue peaks function. As you can see on the image in the left hand side, the small square is representative of a peak in the parameter space, which is a plot of the rho and theta values which are inherent in the parameter space matrix. Now, the hue lines function determines the endpoints of the line segments corresponding to these peaks. It also performs the task of automatically filling these line segments that are detected. On the image in the right hand side, the red crosses indicate the endpoints of the line segments, and the green superimposed lines show the lines that have been detected in the image. Now, moving on to edge detection. The edges in an image are detected using the edge function. When a binary image is input to this function, it returns an image with ones at the positions where it finds edges and zeros elsewhere. Though this function uses the Sobel method of edge detection by default, it can be extended to use other methods as well. This project makes use of the canny edge detection algorithm. The canny edge detection algorithm was developed by John F. Canny in 1986 and is widely used in computer vision algorithms to identify and detect sharp intensity changes which can correspond to object boundaries in an image. The way it works is as follows. It begins by searching for local maxima in the gradient magnitude of every pixel of the given image, which is calculated using the Gaussian filter's derivative. It uses two thresholds, one for detecting a strong edge and one for detecting a weak edge. Weak edges are returned only if the output image has any connected components with the strong edges. Since the scope of this project was to include noisy image, I use this method since the canny edge detection algorithm is able to detect true strong and weak edges with clarity even in the presence of noise in an image. Moving on to the median filter. Images often have a tendency to get corrupted by impulse noise, or as it is known as the salt and pepper noise, which arises mainly due to transmission errors, faulty memory locations, or timing errors. Salt and pepper noise is a type of impulse noise where the pixels either take the maximum value or the minimum value. This type of noise can be easily removed using non-linear filtering techniques such as the standard median filter. The reason why I chose to use a median filter is that it has good denoising power and computational efficiencies. However, some notable drawbacks of this filter are if the noise level is higher than 50%, then this filter tends to lose in the details of the image. Besides this, when the noise level is very high, a larger window leads to unnecessary blurring, while a smaller window may produce insufficient filtering. In MATLAB, the median filter can be realized using the medfilt2 function. This filter scans the image pixel by pixel and replaces each pixel's intensity value with the median of its neighboring pixel values, which is determined by the size of the window being used. By default, MATLAB uses a 3x3 window, but the size of the window can be specified by the user as an argument to the function. Depending on the type of application, the shape of the window can be changed, or the median filter can also be combined with other nonlinear filters, such as max and min filter, to form a hybrid filter. Moving on, another type of noise that can corrupt an image is blurring. Images can be deblurred using the Wiener filter, which works primarily in the frequency domain. Named after its founder Norbert Wiener, the filter attempts to reduce the impact of deconvolved noise at frequencies which have a poor noise-to-signal ratio. In MATLAB, this filter can be realized using the deconv-Wiener function. This function takes in the blurred image, the point spread function, and the noise-to-signal ratio, and returns the deblurred image. The point spread function can be considered analogous to a system's impulse response, which describes an imaging system's response to a point source. If the NSR is made equal to 0, then the process is similar to applying an inverse filter on the blurred image. The Wiener filter works mainly by determining the least mean square error between the estimated and the true image. It is for this reason it is also popularly referred to as the minimum mean square error filter. The reason why I chose to use the Wiener filter is that it produces the best result among other inverse filters in its class, and if a reasonable estimation of the degradation function is known beforehand, then this filter produces a highly satisfactory result. Contrast limited adaptive histogram equalization. This image enhancement technique is utilized because it is an extension to the adaptive histogram equalization and suits the purpose. It involves applying histogram equalization mapping to each pixel based on the values of the pixels in its contextual region. Each pixel is assigned a new intensity value based on its rank corresponding to its neighboring pixels. CLAHE can be considered as an extended concept of regular histogram equalization, where the size of the filter is equal to the size of the image. It operates on small regions of the image called tiles and is particularly effective in removing artificial boundaries or contours. The information from these tiles is retrieved using bilinear interpolation. The image on the left-hand side shows the histogram of the image filtered by a Wiener filter, which has intensity values spread out from 0 to 255. Now, the reason why I chose CLAHE was to remove the gray irregularities that are occurring in the image. Since these irregularities were pushed majorly towards 255 after applying adaptive histogram equalization, as it is shown in the image on the right hand side, this method worked highly in my favor and I was able to obtain a clean and satisfactory image, which resembled the original clean image. Now, the algorithm that I proposed in this project contains the following steps. First step involves reading the image of a clock. Now, depending on the type of noise that is present, we apply the necessary filtering technique, that is, a median filter for impulse noise and a Wiener filter for motion blur. Then, the image that has been filtered is saved. Then, a hue transform is applied and peaks corresponding to lines in the image are detected using the hue peaks function. Colored lines are superimposed on the detected lines in the image using the hue lines function. Using the concepts of coordinate geometry, simple logical algorithm is generated that will determine the time and display this time in the command window. I will now show a small demonstration of my project. This is the code which contains the hue transform and also the algorithm which reads the time from the clock. As you can see, this line represents the edge function which uses the canny edge detector. This line represents the hue peaks function, which determines the peaks in the parameter space matrix. The peak threshold value is given by 0.3 times the maximum value in the parameter space matrix, which is the default value that is used in this function. This line represents the hue lines functions. The hue lines function is used for detecting lines in the image. The fill cap and the min length arguments specify the thickness and length of the superimposed lines. Now I will run this code for a clean image to show that it displays the right time. As you can see, figure 1 represents the parameter space matrix. The small square box indicates a peak that has been identified in this parameter space matrix. Now, in figure 2, the green lines represent the superimposed lines on the hour and the minute hand, whereas the red crosses indicate the endpoints of the lines that have been detected. As you can see, the command window displays 2 o'clock, which is the time on the image. Now, I will show 2 other cases where the image of the clock has been riddled with salt and pepper noise and with impulse noise. Since it was difficult for me to obtain an image which is riddled with these type of noises, I had to resort to introducing the noise myself and then applying the necessary filtering technique and then applying the time reading algorithm to show that it reads the right time. First, I will show motion blur and noise in an image. As you can see, figure 1 represents the clean image of the clock, figure 2 represents the image after motion blur has been introduced, figure 3 represents the image after motion blur and noise has been introduced, figure 4 represents the image of the clock after the parametric Wiener filter applies the de-blurring process. Figure 5 represents the image of the clock after it has been enhanced using contrast limited adaptive histogram equalization. Here the grey irregularities that are observed in figure 4 have all been pushed towards 255. Hence it worked in my favor in cleaning the image of the clock satisfactorily. This image has already been saved. Now I will run the image in the original hue transform algorithm to show that it displays the right time. As you can see, the lines have been detected and the time as displayed on the command window is 11 o'clock, which is correct. Similarly, I extended the scope of the project to a situation where the image is riddled with salt and pepper noise. Clearly, figure 1 indicates the clock image riddled with salt and pepper noise. Figure 2 represents the clock image after it has been filtered using the median filter and contrast limited adaptive histogram equalization has been applied to enhance its contrast. This image has already been saved, which I will run again on the hue transform code to show that it returns the right time. As you can see, the hour and the minute hand have been detected and the time returned is 6:40, which is the time as on the clock. Now I will run this code for random clock images to show that it returns the right time. The time on the clock is 11:55 and the time as returned in the command window is also 11:55. Well, this was the demonstration of my project. Now moving on to the results. The time reading algorithm worked correctly when it was fed with a clean image. When the noise introduced was moderate, the filtering techniques yielded satisfactory results and the time reading algorithm predicted the time correctly. However, when the noise introduced was very high, The utilized filtering techniques were not sufficient as they did not produce a satisfactory result and the Hue transform could not detect the R in the minute hands accurately. However, if better and more powerful image filtering techniques had been applied, then the filtered image would have been much more closer to the clean image and the time return would have been correct. Well, this was my project. I hope you found it informative and interesting. Thank you.